Hello everyone. So in the last video, we had spoken about how to convert a Newman projection into the Sawhorse projection, and we had seen how to figure out the dipole moment of a compound. So dipole moment or a Newman projection, how will you figure out whether the dipole moment is there or not? And I had told you that alkanes don't have electronegativity difference. Hence, no matter we are talking about the gauche or the anti structures, the dipole moment is gonna be zero. Now let's try out for these questions what we have in front of us. Question number 1, 2, 3. Try out these on your own in your notebook. Draw the conformational isomers of these. Basically, conformational isomers, I told you, are the ones which are at the minimum of the potential energy graph. So draw the conformational isomers in Newman and Sawhorse projection, as well as also mark the dipole moment. What do you think is a zero or non-zero dipole moment? Okay, take 2 minutes time, do it on your own, and then I'll discuss the answers. Okay, so these are the answers for the questions. I hope you would have tried it on your own. So there are two kind of representations I was expecting. One was Newman and second is Sawhorse. And I wanted the conformational isomers for these compounds. So as we know that eclipsed cannot be the conformational isomer because it is always at the maximum of the potential energy graph. No matter we are talking about the fully eclipsed or we are talking about the partially eclipsed. So here, these are the two forms we have. One is anti, another is gauche, which will be considered in the conformational isomer. So this is how your anti will be, where all this where the same groups will be completely opposite of each other. This is one. And gauche is where the arrangement can be anywhere. So I have written fluorine, fluorine here, hydrogen, hydrogen, hydrogen. This is your gauche. Now the same thing can be represented in the Sawhorse also, and I told you how to write a Sawhorse representation. So this is your front carbon, just write it as it is, remove the circle behind, show the bond, and then this is your back carbon, and just exactly same thing you have to write. Hydrogen here, fluorine here, just write hydrogen, hydrogen and fluorine. Similarly for gauche, this is our Sawhorse representation. So in the front carbon, fluorine, hydrogen, hydrogen is mentioned. So fluorine, hydrogen, hydrogen. On the back carbon, hydrogen, fluorine, hydrogen. Exactly same way we have written hydrogen, fluorine and hydrogen. Now we have to see whether they have a zero dipole moment or non-zero dipole moment. So when I'm talking about anti, there is just one group, that is fluorine. It's not even a molecule. It's not like multiple atoms are attached over here. So when you will talk about the dipole moment will be zero because the dipole moment will be in the opposite direction. Okay, now when you're talking about gauche, in this case, is the dipole moment gonna be zero? No. Why? Because the dipole moment will be this and this. So overall sum is gonna be more than zero. So these are just vector additions. You can just understand. You have seen dipole moment questions earlier also. I think by now you will be much comfortable in figuring out when the dipole moment is gonna be zero and when is the dipole moment gonna be non-zero. Okay, now exactly same thing will happen for CH2Cl, CH2Cl. That's the reason I have just not drawn it over here. Now come to CH2 fluorine and OH. So here actually there is no exact anti-structure. Why? Because the same groups are not appearing. So here only thing is the two groups, the two different functional groups can be opposite to each other or can be next to each other. So that's how the process can be. So we can't call them exactly anti because in anti the same groups are generally opposite, but at least the groups which are most repelling are opposite to each other. So this is like anti but not exactly anti, so we just don't give them any name. Okay, so these are two conformational isomers we have. Here the two repelling groups are closer to each other, here the two repelling groups are opposite to each other. Now when I have to find out the dipole moment, in this case this dipole moment of this molecule is also gonna be non-zero. Why? Because first of all, these two groups are not same. Secondly, OH is not a linear group. OH is generally either like this or OH you can write it like this. That's how the OH will be. So the direction is not completely opposite. Direction is a vector, direction of dipole here is a vector addition, and so it is non-zero over here. Okay, when you talk about stability of the molecule, your the second molecule in which F and OH looks closer, basically gauche representation, that is going to be more stable, though it is highly unlikely for most of the compounds. But here in this case, why your second representation, which is gauche, is more stable than the first one? Because here the stability is due to the hydrogen bonding. So hydrogen bonding brings a very a strong stability in the molecule. So here fluorine and OH will do the hydrogen bonding, which will make this whole molecule better stable than the first one. Okay, so this you have to look at, and this is very important. So they ask you these questions. I mean, they give you different conformers and they ask you which one is more stable and so on. So here you have to see whether the possibility of hydrogen bonding is there or not. By the way, dipole moment is not something which is affecting the stability, because for both the dipole moment is non-zero. Gauche, I have not drawn. I was expecting that gauche is something which you guys know how to draw it. So if you want me to draw it, I can draw it very quickly over here. So this is your fluorine, hydrogen, hydrogen, and then hydrogen, hydrogen, OH. That's how you have to write for this molecule. And for this, you have to write it as fluorine here, hydrogen, hydrogen, then bond, OH, hydrogen, and hydrogen. So this is gonna be my Sawhorse projection. Okay, now let's see a few more questions. Try them out again on your own, because I have explained you these two questions. So on the basis of that, try out doing the other questions also. Okay, try out the question number 4th and 5th, and then I'll discuss the answers. Okay, so now let's see the answers of these questions. So first molecule, what we have is CH2OH, CH2OH. If I have to draw the representations, or you can say the conformations of these of this compound, so we have two. One is gauche and another is anti. Right now we have to see whether the dipole moment is zero or non-zero. So in this case, it is very clear that the dipole moment will be non-zero. Both the OH are upwards. You talk about this, looks like the same groups are opposite to each other. Are these going to give you a zero dipole moment? No. Let me tell you why. Because OH is not the linear group. So representation of OH will be in two ways. When you talk about OH can be in these two ways. In the group of the molecules can be arranged or aligned in such a way. Look at this. So here is how molecules can be aligned. So if this is the case, then what is going to happen? Mu is going to be non-zero. If this is the case for few molecules, so few molecules will be aligned like this and few molecules will be aligned like this. When they are aligned like this, then your dipole moment can be zero. But if they are aligned like this, the dipole moment is going to be non-zero. So total dipole moment of this compound is going to be non-zero. So non-zero dipole moment for this, even though it looks like the same group is opposite, and the dipole moment should be zero. Now when I talk about the stability, which is better stable, the gauche is better stable due to the hydrogen bonding again. Okay, so this funda you have to remember. Look at the next compound. We have CH2NH2 CH2F. I can write it like this. Again, one is anti-like conformation, and there is gauche conformation. So here this is your structure. Again, both of these will have non-zero dipole moment. I hope I need not to explain you why non-zero. Now here in the gauche, again they will have what? Hydrogen bonding, and hence it will make it more stable. The stability does not depend upon anti or gauche. It depends upon what all other factors are also present there. So you will not just go by one straight line that antis are more stable than the gauche. You will check it, these factors also, whether hydrogen bonding is present or not, and accordingly you will answer. Now look at the next compound. You have to find out the most polar conformer for this question. We have CH2, CH3, CH2, Cl. So we have, if we have to draw, we will draw it like this. CH3 up here, this is the first carbon, this is the second carbon. So one conformer is anti-like, I should not write anti, but yeah, anti-like conformer. And second is gauche conformer. CH3 and Cl are opposite to each other. It is anti. It is in the form of anti, by the way. It's not anti, but it is in the form of anti, where these two repelling groups are opposite to each other completely. And general behavior is, or general saying is, that the antis are more stable and they have zero dipole moment. But look at it. It has much more or much greater dipole moment as compared to the gauche. Why? I think I have written something wrong over here. I think it should be not chlorine, it should be hydrogen. Okay, please correct it. Okay, this is hydrogen over here and chlorine is here. So here both of these vectors are adding and increasing the dipole moment drastically, whereas in this case, when you talk about the dipole moment is like this and then like this. So relatively lesser dipole moment is there. So when they'll ask you which has the more dipole moment, the anti representation of it has more dipole moment than the gauche representation. Okay, so now let's write some important points on this, what we have learned and observed in the molecules till now. So if I have a molecule with two functional groups attached on the first and second carbon, mu will be 0 only in two cases. One is if Z is monoatomic, that means chlorine, fluorine, bromine, iodine, such kind of things are there. So if the Z or the functional group is monatomic, then your mu can be 0, or when the Z is a linear group. Only in these two cases, when they are in the anti position, they will have a 0 dipole moment. Apart from these cases, other cases will have non-zero dipole moment. So let's see, this is the example I have given where two fluorines are there which are monoatomic. Then I have given you an example of CH triple bond, C triple bond H and C triple bond H. This is a linear group, and that is the reason why mu is 0 over here. Exactly same way, cyanide group is your linear group, and that is giving you a 0 dipole moment when they are positioned at the anti positions. Now exactly same way, if I have a molecule with COO minus, so this COO minus, and there is a difference in COO minus and COH. So if I'm drawing CO minus, this is how exactly I'll be drawing it. CO minus will be O, and the negative charge will be dispersed between this oxygen and this oxygen. Exactly same way, that's how the COO minus will be represented when it's on the lower carbon. So basically anti positions, this is how COO minus will be represented. Negative charge will be completely dispersed between one oxygen and another oxygen because the resonance is happening. Okay, so in this molecule, if you'll see, then the dipole moment is gonna be 0. Okay, because the shape is exactly same. It's almost like a linear. The negative charge is completely dispersed. So when you're talking about COH is written like this. This is not a linear group, and the resonance is behaving differently. It's not the equal resonating structures what it is forming as in the case of CO minus, and hence the dipole moment is gonna be non-zero. Okay, so this is something which is very important. You have to understand, you have to make a note of it, and whenever you are solving a question, look at these factors while marking for the dipole moment. Now the next part which we are going to understand is conversion of Newman projection to Fischer projection. This is very important part, and this part you are not going to do only in this chapter, but you are going to use this part in the biomolecules and other chapters also. Now we know how to represent a Fischer projection individually when we have got wedge and dash structure. We know how to represent a Newman projection, and now if I have to just make a relation between Newman and Fischer, we have to see how to convert one into another. Okay, before we start Fischer, there are a few important things which you have to understand. First thing is, Fischer projection is only meant for eclipsed Newman. So whenever there is a staggered Newman, you cannot directly make a Fischer projection out of it. You have to do some changes in the structure, and then only you can convert it to Newman. Okay, so Fischer projection means it's an eclipsed Newman. So no matter when you're converting Newman to Fischer or Fischer to Newman, you have to keep this thing in your mind. When you're converting Fischer to Newman, then the Newman projection what will form will be eclipsed. When you are converting your Newman to Fischer, in that case also you have to get the eclipse structure first and then convert it to Fischer. Okay, so let's see what all different ways are there. How can we convert a Newman into Fischer projection? So let me just give you a brief idea first without explaining what is written on the slide. Now let's say I have a molecule like this. This is my molecule. This is my eclipsed representation of a compound. Okay, now if I have to convert it into Newman, what will I do is, look at the front carbon. This is my front carbon. Okay, so this front carbon, what all attachments are there? CH3 is attached, hydrogen is attached, and OH is attached. So this is gonna be my front carbon. Okay, and exactly same way how the molecules are placed in the Newman projection, exactly same way you have to place it on the your Fischer projection. Okay, so CH3 is on the top, then H on the left, and OH on the right. Simple. Now the other carbon, the back carbon, is the second carbon. This is your rare carbon, and it has CH3 attached. So let's put the CH3 down here, and rest of the attachment will remain exactly same in the direction. So OH is on left. Let's write OH on the left, and hydrogen is on the right. So let's write the hydrogen on the right. As simple as that. That's what you have to do when you are converting your Newman to Fischer when the eclipsed is given. Okay, now if let's say eclipsed is not given but the staggered is given, then what we will do, There are multiple ways we can approach. Okay, one way is, okay, this is my staggered. So what will you do in this case? In this case, you will again treat it the front and back carbon in exactly same way. Front carbon configuration is CH3 hydrogen OH. You will write it as CH3 hydrogen OH. Okay, and for the back carbon, what you have on the downer plane, you have OH, and then what you have, hydrogen and CH3. Now switch their positions. You have to switch their positions, and then you will write it on the Fischer projection. So here you will write it as CH3 and OH. Okay, now you have to, just in case, see whether it's the same molecule or it has become a different molecule altogether. See here, this is the same molecule, right? I have just rotated it to 60 degree and I have got exactly this. Now you can just confirm with your Fischer projection. Double switch must give you the same compound. See, compound is not changing. This and this is the eclipsed and staggered form of the same compound. So basically Fischer projection should also not change. The RNS configuration should also not change. So let's see whether what is the configuration over here in the first case. So this is 1, then this is 2, the downer group is 2, and then 3. So I am going from 1 to 2 to 3. This is clockwise, so it is S. And if I write it this way, 1, then 2, and then 3, I am going clockwise again. 1 to 2 to 3, yes, I'm going clockwise again, and this is again S. So S is the configuration for my upper one. I wanted to draw the staggered of this, and actually I have not. Okay, let's do one thing, just ignore this one, and staggered for this I'll draw here. Though how to represent staggered into Fischer, I have explained you, that is not gonna change, but I just wanted to show you that no matter you have a staggered conformation or the eclipsed conformation, the Fischer projection will give you the same RNS or same configuration, and that will remain same. It is not gonna vary. So I think I have done a small mistake when I move it to 60 degree. This will be OH here, H here, H here, and OH here. This is the correct staggered representation. For this, I think the RNS, the configuration on the Fischer would be different, because I had put OH and OH over here. So please ignore this one. Now again, convert it to Fischer first of all. So this is my CH3 on the front carbon, and then I have hydrogen and OH. So exactly same way I'm going to place it over here. Then on the back carbon, so hydrogen is down here, so I have put hydrogen here. Now there are two groups, OH and CH3, switch their positions. So CH3 comes here and OH comes here. That's how the molecule would be. I hope I have done everything right. Let me just quickly check. CH3, H and OH, H, CH3 and OH. Yes, now we can start finding out RNS for it. So this is 1 and 2 and 3. So 1 to 2 to 3, it's clockwise, so it is S. And now again 1 to 2 to 3. Yes, 1, 2 to 3. So this is anti-clockwise, and this is hydrogen over here on the vertical plane. So it is S again. So SS configuration for this, SS for this. So that means their Fischer is exactly same, no matter your Fischer. These are identical Fischers, right? I mean, you can just do a double switch and you'll get the exact same thing. The Fischer is not gonna change no matter you take eclipsed or staggered, but how to write it is gonna be a little different way. So whenever you're talking about staggered, what you have to do is you have to switch the positions of the things which are present on the back carbon, and then place it on the Fischer projection. This is one way. Okay, this is one way, and this is a quicker way. Let's figure out what is the another way of representing staggered into Fischer projection. So the other way is you take the staggered conformation. Okay, now look at this molecule. This is staggered conformation. What we will do is we will rotate it 60 degree anti-clockwise, so that CH3 comes just behind each other, and this becomes eclipsed. Okay, so this is my eclipsed representation. Now OH is behind H, hydrogen is behind chlorine, and CH3 is behind CH3. I have got an eclipsed structure now. Now just place it on the Fischer projection. So what we will do, front carbon is this one. So I have CH3 hydrogen and Cl, CH3 hydrogen and Cl in exactly same way I have put. On the back carbon there is a CH3, CH3 I have put it over here. OH is on left, so I have put OH on the left, and hydrogen is on the right, so I have put a hydrogen on the right. This is another way. One more way is there when the staggered is given in a little different manner. When the back carbon is has the groups pointing upwards like this, and the front carbon is like this. So this is also staggered, right? Just look here, CH3 up and hydrogen chlorine down. Here I have what we have done, CH3 is down, hydrogen bromine up. So a bit of difference in the representation of staggered. So if this is how it is given, what you will do is you will rotate it to 180 degree. This always rotation has to happen on the rear carbon, not on the front carbon. So rotate this CH3 to the 180 degree, bring it down. So I have got CH3 down here. Now this what all we have, this OH will go towards hydrogen. So basically OH is behind hydrogen and hydrogen is behind bromine. So that's how exactly it will look like. Okay, so now what we have to do, now we have to just directly place it on the Fischer projection exactly same way how we had drawn it before, but there is a difference on the Fischer projection. Earlier the top carbon was a front carbon and the next carbon was a back carbon. Now the upper carbon is the back carbon and the lower carbon is the front carbon. Okay, because it is inverted basically. Okay, so now the top carbon here, whatever the intersection is, that chiral carbon is the back carbon. So back carbon has what all present on it? Back carbon has OH on it and hydrogen on it. OH is on left and hydrogen is on right. So OH is on left, hydrogen is on right. On the front carbon, what we have is CH3. So hydrogen is on left and Br is on right. So hydrogen is on left and Br is on right. Only difference in these two representations is, in one the front carbon is up and back carbon is down, and if your staggered is inverted as in, instead of it's being this, it is like Y, in that case your Fischer is also inverted and your down carbon is front carbon and top carbon is a back carbon. Okay, or I told you what is the other way for staggered. Let's draw it quickly over here just using that method what I have explained you just now. So I can just simply put it over here. This is my CH3, so let's place it over here. CH3 is here, and then I have what all on CH3, hydrogen and chlorine. So I have put hydrogen and chlorine. Now what else is there? Hydrogen down here, and then I have to switch the positions of OH, CH3. So CH3 is here and OH is here, right? Now if I have to see whether this and this Fischer is same or not, just do the double switch. Bring hydrogen here and then do the switch between OH and hydrogen. So OH will eventually come here, hydrogen will come here, and CH3 here. Exactly same Fischer it is, and its configuration is also gonna remain exactly same, so it's not gonna change. That's how you have to convert your Newman to Fischer. I hope you have got it. Let's try out some questions. Okay, so I have taken this compound COOH, HOH, HOH and COH. This is my meso Fischer. Look at it. This is a meso compound. It has a plane of symmetry. If I'll draw its Newman projection, this is my front carbon. The placements are COH, H and OH. The placement here is COH, H and OH. On the back carbon again, COOH right here, H on the left and OH on the right. I have written it in the exactly same manner. Now what we'll do is we'll try to rotate it through all the angles, and we'll see different kind of fissures it is forming and different type of Newmans it is forming, and we will see whether rotation is bringing any change in the configuration of the molecule or not. Rotation of the Newman projection and the look wise, what Fischer looks different, is it actually different or not? That is what we have to check very quickly. Okay, so what I can suggest you is, rather than waiting for me to explain everything, you better stop the video, take this molecule. I have given you the fully eclipsed molecule, and what you do is rotate it to 60 degree, 180, 240 and then so on till 360. Draw all the Newman projections and then draw their Fischer. It is a good practice for you. Secondly, once you'll be done with this, you can quickly verify with my thing, and we will see whether there is any change which is coming in the molecule due to the rotation or not. So try it out, pause the video, do it on your own. Okay, so I'm hoping that you would have done by now. So let's quickly see what has happened. If I rotate it to 60 degree, what will happen? COH will come here, OH of the back carbon will come here and hydrogen will come here. So this is after rotation of 60 degree. Now let's write it on the Fischer projection. I told you I prefer using the first method which I told you for staggered conformation. What is that? I'll just place the groups exactly and just swap the groups. That's all is what I'm gonna do. But you can use whatever method you want for converting a staggered into Fischer. Okay, so this is my COH right here, hydrogen and OH. So this hydrogen and this OH has been placed. So on the rare carbon I have OH over here, so let's place OH over here. And then what else I have hydrogen and COH. Swap their positions. So COH is here on right, here I'll write it on left, and hydrogen is on left, I'll write it on right. Okay, so this is this thing. Then rotate it to 120 degree. So COH will come behind OH, hydrogen will come behind COH, and OH will come behind hydrogen. Now if I'll place it on the Fischer projection, what is it? Top is COH, written COH, hydrogen and OH is on left and right of the front carbon, hydrogen OH on the left and right of the front carbon. Look at the back carbon. What I have, hydrogen down here, and then I have what else? I have OH and COH. So exactly same way I'll write it on the Fischer. So OH and COH over here. This is, so right now I'm just writing all the Fischers and Newman, and then we will start comparing. Exactly same way I have done a furthermore rotation. This is my Fischer for it. COH, H and OH, then COH. So swap the positions, and then OH and H. Do the 240 degree rotation. COOH on the top, H and OH, and OH on the bottom, COH and hydrogen. Okay, then again rotate it, and then what I have is COH, H and OH. So I have written COH, H and OH, and then down here is hydrogen. Okay, then swap the position. COH on left, I'll write it on right. OH on right, I'll write it on left. Okay, again rotate it, and I'll get COH, COH, COH on the top, and H and OH here, H and OH here, COH down here. What you have is hydrogen on right, hydrogen on left, and OH on right, hydrogen on left, and OH on right. That's how exactly we are going to place it. So placements are done. Now we have to see whether the configuration is changing or not. Look for the first one. As I told you, this is a meso Fischer. This is optically inactive. So I also want to check whether any of these molecules or any of this rotation will make them optically active. Is it gonna be any change in the molecule? Let's see. So R and S configuration on first and second carbon after rotation, I have got again R and S configuration. Okay, again R and S configuration, again R and S configuration, here also R and S configuration, here also R and S configuration, here also R and S configuration. So throughout the configuration is exactly same. If the configuration is same, that means what? The molecules or these structures, the Fischer projections are identical. These are identical, these are exactly identical. And if they're all identical, then what do you mean? Then all of these are meso and all of these are gonna be optically inactive. You just have to do the double switch, bring it into the place so that you can see the plane of symmetry. That's all you have to do. So basically rotation of the molecule is neither gonna change its configuration, okay, and nor its optical activity. That's what exactly I wanted to say. So all of these are identical, all of these are optically inactive. So a compound, if a compound's Fischer projection has been given, no matter you make it, if a Fischer projection is given, you write it eclipsed form, you write a staggered form, or you write whatever form. If the molecule is meso and optically inactive, rest of the all representations are also gonna be meso and optically inactive, no question about it. So we have seen a representation over here just now. Okay, now if I do a small change in this molecule in the configuration, and then let's try the same pattern, same Fischer projections I'll draw, same way I'll draw the Newman projection, and we'll see again, is there any change possible in the configuration over there? Right now I have shown you the meso structure. Now let me take an enantiomer of this molecule. Enantiomer as in now the optically active compound of the same structure. So by making small change in OH and hydrogen position, I will get a compound which will be optically active. So let's see if I'll draw its Newman, and if I keep rotating them, draw different Fischers, is it gonna make any change in the molecule or not? Let's quickly see. So this is the molecule which I have given you. It's exactly same molecular thing is OH and hydrogen position I have just swapped. Earlier the OH was here and hydrogen was here. Now I have put OH here and hydrogen here, which is bringing the configuration to R and R. Earlier it was R and S. So earlier was meso, and this one is not meso. This one is a normal optically active compound. Now what you have to do is, rather than me doing it for you, try out on your own. First of all, convert it to the right Newman projection, and then do the rotation for the Newman projections, all the rotations possible, and draw their Fischer projection and see if there is any change you can see in the configuration of any Fischer projection. If this is optically active, are all gonna be optically active, or is there anything which you can get as meso or something in middle of rotation or something? So just check it once and then we will quickly discuss. Okay, so I have drawn the structures over here. I'm not gonna take much time. I'm gonna finish it very fast, okay? Because I'm hoping that you guys would have done it. So this is my molecule. I have drawn its Newman. So what I have done, this is my front carbon, COH, H and OH is present, COH, H and OH is present. I have drawn this as, this is the back carbon, so COH. I told you always have to assume that your Fischer is a eclipsed structure. So you have to write it in the eclipsed form. So COH here, OH on left and hydrogen on right. So that's how exactly I have written. Rotated it to 60 degree, got this. And if I'll draw its Fischer, it will be COH on the top, then hydrogen and OH, and then hydrogen down here, and then switch the positions of COH, OH. So COH here and OH here. Then again rotate it for 120 degree. So that's how I think I have missed writing it over here. So this is my COOH. For all the molecules I have drawn it like this. Please check your structures. Meanwhile, let me just finish this off. COOH, H and OH, and then OH down here, and then swap the position of COH and H, so hydrogen here and COH over here. Okay, so these are the structures which we can get by rotation for Fischer as well as for Newman. Now we will see their configuration is varying or not. Look at the first one. So here I have already got RR. Here in this case 1, then 2, and then 3. So anti-clockwise it is R, 1, 2 and 3. Anti-clockwise again it is R. So configuration is same. Let's talk about this. This is 1, 2 and 3 down. So this is R, 1, 2 and 3. Again this is anti-clockwise and this is R. So till now RR configuration. Here again let's see 1, 2 and 3 down there. So this is actually the front carbon is fixed, so its configuration is not gonna change. If it is gonna change, it is gonna change for S, if at all it is gonna change. This is 1, 2 and 3 on the top, so anti-clockwise again. So this is R, R for the top, 1, 2 and 3. Again this is anti-clockwise, this is R, then R for this, then 1, 2 and 3 again anti-clockwise. This is R. This is R, I already know this as it is fixed. Then what is it? So this is my 1, 2 and 3 again anti-clockwise. This is R. So configuration is also exactly same. It's not changing. So no matter you take an optically active compound, eclipsed Newman or staggered Newman, whatever you will take it, it is gonna show you the same configuration, same optical activity. It's just a way of representing the molecule is a little different because they are rotating all the time, but that doesn't make any change in their configuration. That doesn't make change in their optical activity. Optical activity and the configuration is gonna remain exactly same. Okay, now let's understand 2-3 terms. Why those terms are important? Because you will get 2 random compounds and they'll ask you to compare and find out the relation between them. Okay, and those compounds can be in the form of Fischer projection. If Fischer, then you already know how to find out the relation. If the compound has been given in the Newman projection, then you will have to convert it to Fischer and then find out the relation between them. Okay, so let's quickly see. So there are a few terms which we'll quickly revise, which we have done earlier, and I'm just giving you a quick brief so that to make sure that you have not forgotten them, and we will use it in the questions now. So there are 2 types of isomers. One is configurational isomer, another is conformational isomer. I think I have done a small mistake of a spelling mistake over here. So configurational isomers are the ones which are different and isolable. These are configurational. Basically, their configuration is different. Conformational isomers are identical and non-isolable because they are conformers of each other. So they are gonna be identical. Okay, just use this, just remember this and use it. Configuration means change in configuration. Conformation means change in the conformers, where conformers are non-isolable and identical. Okay, enantiomers are the ones which are non-superimposable optically active mirror images. Mind it, these are optically active. If it is optically inactive, then won't be considered as enantiomers. Diastereomers, these are non-superimposable non-mirror images. One can be optically active, one can be optically inactive, both can be optically inactive, both can be optically active, any combination can be there. Okay, now let's say if I ask you to go and relate back to the compounds which we have discussed just now, what I have done is I have taken the compound 6 of question 1 and 2. Question 1 and 2 is the one where I had taken R and S configuration, that is meso thing, in the first one, and RR configuration for the second. Let's see what are the first and second compounds over there. Okay, let's go back to the older slide. Okay, so this is, I think I wrote it on a wrong page and it got rubbed off. So this is HOH, OH here, and then hydrogen here and COH here. Okay, this is one thing, and this is my first compound, second, third, fourth, fifth and sixth. So exactly this one is the thing which we are looking for. So two hydrogens on same side, COH, OH, OH, COH. This is one compound. Okay, now let's move to this the first question and see what is the compound over there. This is my sixth compound. This is first, this is second, this is third, this is fourth, this is fifth, and this is sixth. So yes, this is my sixth compound. So in this compound, what is the configuration? Just look at the configuration, because I don't think I can remember the compound by the time I'll explain you on the other slide. So the configuration here is R and S, whereas the configuration for the previous sixth one was R and R. That's all we have to check. Okay, now let's find out the relation between them. So I don't remember the compounds exactly, but you can definitely check it in your notebooks, and we can just talk about the configuration mentioned, because the compound was same, we knew it. This question 1 and question 2, sixth compound will, first one has R and S configuration, second has R and R configuration. So if second has R and R configuration and first one is R and S, they are, one is optically active, this was optically inactive, and this is optically active. We know this first compound was optically inactive, second was optically active. So obviously these are not mirror images of each other and non-superimposable. Moreover, one is optically active, one is optically inactive. So what is the relation gonna be? Are they gonna be same or different? First of all, there is a difference in the configuration itself. So they are the configuration. Why? Because you can see RRRS. So configuration is different. So configurational isomers. And then if I have to find out whether they are enantiomers or diastereomers, they are gonna be diastereomers. Why? Because one is optically active and another is optically inactive. Secondly, they are non-mirror images of each other. So configurational and diastereomer is the relationship between the first compound first question sixth compound and second question sixth compound. Okay, now if I have to talk about the first question again, and then I have to talk about anti compound of it and the sixth compound of it. See, first we have discussed in the first question we have discussed all the things properly, that the configuration is not changing throughout. Okay, even though the Fischer looks like it is different, but if you find out the configuration, you'll get to know that the configuration is maintained throughout, and the whole thing is optically inactive. So no matter whichever compounds you compare, or no matter whichever forms you compare in question number 1, all of those forms are exactly same. So these are identical. So what we will call them? We will call them, these are conformational. Why? Because these were identical, and they are diastereomers. Why? Because they are not superimposable. You look at the images and you'll get to know that these are non-superimposable. Okay, so conformational diastereomers are non-isolable. Mind it, because the term conformational means non-isolable. Okay, now if I take the second question, compare anti and any other random compound, again the same thing is there. So their Fischer will look different. It will look like it is non-superimposable. So diastereomers is actually not right a term when these are non-superimposable, when these are conformational, because actually these are identical. So you can just swap and then swap the positions and you can get the exact same thing. So anti of the second question and sixth compound of the second question are conformational isomers, and we call it diastereomers just on the basis of whatever has has been given over there. Basically, when you look at the Fischer projections, though the configurations are exactly same, the Fischer projections are non-superimposable right now. So we have just mentioned them, diastereomer. Okay. Minded diastereomers and enantiomers are ideally the words which are used for configurational, must not be used for conformational. But many times the questions have been asked in this way. They are taking the literal meaning of diastereomers. They are just comparing the Fischer projection and seeing whether it is superimposable or not. Ideally, conformational isomers are just conformational isomers. These are not diastereomers. Okay, why? Because diastereomers are the ones which can be isolable. Their configurations are different. They are non-superimposable. So there are many things. So it doesn't suit the diastereomer definition at all. If it has been given and asked conformational diastereomers, then conformational automatically means these are identical, and diastereomers, they are just giving you the term diastereomers in reference to the whatever Fischer projection they are looking at, whether that is superimposable or not. They are not swapping, they are not bringing it to the same thing and so on. Okay, now you have to find out the relation between these two exactly same way how I have given you. Try it out on your own and then I'll quickly discuss. So this is my answer. Let's quickly check. This is the already given Fischer projection. I have to convert this molecule into Fischer. So what is the Fischer over here? CH3 I'll write up here, hydrogen, chlorine here. Now CH3 down here, and then swap the positions of chlorine and hydrogen, chlorine on right and hydrogen on left. Let's write down their configuration. S for the above one, R for the down one. Here it is S and S. So obviously it looks like both of them are both of them have the different configuration. Let's see whether this compound has a plane of symmetry. So this is meso and optically inactive. Whereas when you talk about this has a pretty good optical activity. Both chiral centers are here, and this doesn't have plane of symmetry, no center of symmetry. So this is optically active. This is optically inactive. Difference in the configuration, non-superimposable images. So this is configurational diastereomers. That's how exactly you will figure out the relation between two compounds if they have been given one in Fischer projection and another is Newman, or both are Newman or both are Fischer. Fischer you already know how to figure out, but in case of Newman you have to convert it to Fischer and then find out the relation between them. So here we have done some questions. This whole video was about the questions and knowing small details of them. In the next video we'll talk about the conformations of cyclohexane, which is an important part, stability factor in the different conformers of cyclohexane, and then many more things. Okay, so next video mostly is gonna be the last video for conformational isomers. Till here, if you have any doubt, ask me in the doubt session. Try solving the questions from your module and book. Topic is very easy. Try to understand. Do not try to mug up. The only thing which you have to do over here in this whole thing is converting Fischer to Newman and Newman to Fischer. That's all. Rest of other things you've already learned in optical isomerism, and all these concepts you can put it over here whenever it has been asked for optical activity, diastereomer, enantiomer, so and so thing. There is no much add up to the knowledge in this chapter apart from knowing how the rotation in the molecule happens and how it is represented in two representations.